Okay, we're finally ready at this point to talk about logarithms. And this definition, I think, is a little weird to a lot of students because it's the first time a lot of people have seen something defined this way. In the past, whenever we've defined a function, it's all been in terms of so-called elementary operations: addition, subtraction, multiplication, division, exponents, that kind of thing. Essentially, it's been a formula, right? Well, that's not how logarithms work. Logarithms are defined to be the inverse of an exponential function. Right? So if we start with an exponential function like, and I'm all the way down to the last sentence here. If we start with an exponential function like x equals a to the y, right? Well, the inverse of that is y equals the inverse function of x. And the inverse function of x, the inverse for the exponential function, is what we're going to call a logarithm. And we're going to abbreviate that log. Like I've got it here in the second line. Now, I know that maybe still seems kind of weird, right? So let's look at some examples. Right? I think it gets a little clearer if we do that. So let's say I have something like y equals the log base 5 of 25. Well, look at what the definition says. The definition says y equals log base a of x is equivalent to x equals a to the y. Okay, well, so let's make that switch. Right? I'm going to keep the bases the same. The base of the logarithm, base of the exponent, those are both a, so they're both going to be 5 with my expression here. And the other two variables change sides. Right? The y becomes the exponent. So what I'm doing is I'm looking for a solution to this equation. Right? What value of y makes 5 to the y equal to 25? Well, hopefully it's clear to you. That's 2. So that is the log base 5 of 25. Right, so let's try another one. Right, log base 16 of 4. Well, do the same thing. This is equivalent to asking 16 to what power is 4. This one you may have to think about it for a minute. Remember, fractions are allowed here. Right? Nothing wrong with decimals. The square root of 16 is 4, and the square root as an exponent is 1/2. Right, so the log base 16 of 4 is equal to 1/2. All right, so how about another one? Now, you don't really necessarily want to walk through all of these steps. You might do this a little in the beginning where you're just getting the hang of it, right? But when I look at something like this, what happens in my head is I say, okay, this is asking me what power do I have to raise 12 to get 1? In other words, 12 to what power equals 1? Well, to get 1, you have to raise something to the 0 power. Right? So there you go. That is the log base 12 of 1. In fact, that's the log of any base of 1. It is always going to be 0. Okay, so how about this one? All right, well, think about what we're asking for here, right? This is saying 6 to what power is -2. Well, you can't raise something, you can't raise a positive number to a power and get a negative number. So you can't do this. In fact, let me generalize. You cannot take the logarithm of a negative number ever. Okay. So let's look at some more examples here. Say we have log base 3 of x equals 5. Okay. I want to convert this. Here's the question you might be asked, like on a homework assignment or a test or something. Convert this logarithmic equation to the equivalent exponential equation. Right? And the way I think about this, right? Remember, the bases stay the same. So it's going to be 3 to a power. And the other two parts switch sides. So the 5 is going to come over to the left side and become the exponent. The x is just going to go over to the other side, and it's still going to be an x. Okay, but 3 to the 5th, that's a number, right? You see, 3 to the 5th power is 243, right? So there's my answer, x equals 243. And I want you to think about what we just did right here. Right? What we just did right here is we just solved this exponential equation, this logarithmic equation. And you'll see as we go along, and we're going to talk about equations again. This is the fundamental technique that you're going to use to solve logarithmic equations. You're going to convert it to an equivalent exponential one. Okay, so how about this one? Okay, that looks a little weird, right? There's no base. Right? There's no base down there, a little subscript between the log and the x. Okay, there is a default base. Just like with square roots, if you don't put an index up there, it's a second root, right, instead of a cube root or a third root. Just like that x there, it has an exponent. It's a 1. That's kind of the default, and we don't write it. Logarithms are the same way. Logarithms have a default base. If no base is specified, then this is base 10, right, which is a so-called common logarithm. Right? So my conversion here is going to be x equals 10 to the y. Base stayed the same. The x and the y switch sides. Okay, let's try one more here. ln of 5. Once again, not only is there no base, this time it doesn't even fully say logarithm. This is the so-called natural logarithm. Right, you remember a couple lectures back we talked about a new special transcendental number, e. Right? ln, the natural logarithm, is the log base e. So my translation of this would be e to the y equals 5. Okay, so how about going the other way? Right? How about taking an exponential equation and turning it into a logarithmic equation? Same set of rules. Right? Same set of rules. The base stays the same. So this is going to be log base 3. The 81 and the 4 change sides. There you go. 3 to the 4th equals 81 is equivalent to the log base 3 of 81 equals 4. Okay, so how about this one? 4 to the x equals 12. Well, base of my logarithm is going to be 4. The 12 goes into the logarithm. The x goes over to the other side. And I went ahead and switched it, right? Because we always want to have the variable part on the left and the number part on the right. So x is equal to the log base 4 of 12. And again, I want you to think about what we just did right here. Right? We just solved that exponential equation. Because the log base 4 of 12 is a number. Right? It's a weird number. It's a transcendental number. It's in the same category as e and pi. But ultimately, yeah, it is just a number. Right? So that would be the solution to this equation. We'll talk a little bit more later on about how to actually turn that into a decimal number. Okay, so how about the domain and range of these things? Well, we saw several lectures back that the domain of the exponential function was all real numbers, and its range was non-negative real numbers, right? Everything from 0 and up, not including 0. So what does that make the domain and range of the logarithm function? Well, remember, they're inverses. The difference between a function and its inverse is the x and the y switch roles. Well, the domain is all the possible x values. The range is all the possible y values. If we switch those, we get the range of the logarithm is all real numbers, and the domain is the non-negative real numbers. And that matches with what we saw a couple slides back, right? This domain is saying you cannot put a negative number into a logarithm. It's not defined for negative numbers, right? Which is what we talked about a little bit earlier. Okay, so before we wrap up here, I have a couple special relationships that I want to look at because they're important, or they're going to come up again from time to time as we go along. My question is, what are f and g are a logarithm and an exponential function? And my question is, what are f of g and g of f? Well, from what you know about inverses, you know just right off the bat, those are both equal to x. Because if you take the composition of a function and its inverse, that's what you get. Okay, but this gives us two kind of interesting formulas. Suppose we actually take the composition of these functions. Right? For example, for the first one, take a to the x and put it into that logarithm. Right? If we do that, we get the log base a of a to the x is equal to x. In other words, in a sense, that logarithm and the exponential, they cancel each other. It's kind of like earlier, you think about when you had the square root of x squared, that was equal to x. because the square root and the exponent, they kind of canceled out. Really, they were inverse functions, right? Which is really why that works. But it's the same thing going on here, right? Exact same thing. Now, that one isn't too bad, because remember, if you just think of this as the logarithm side is saying, what power do I have to raise a to get a to the x power? Okay, yeah, that's x. Not a problem. This other one is a little less intuitive. If we do the same substitution, if we take the log base a of x and replace the x in the exponential function with it, we get this. A to the log base a of x is equal to x. I don't have a really simple explanation for why that's the case, like I did with the first one. In this case, it's just they're inverse functions, right? So does it look kind of weird? Yes, absolutely. Nevertheless, right, that is a true, always going to be a true statement. Okay, now I've got the basics of logarithms down. We're going to get some more practice. We're going to be using some of these things quite a bit as we go along, so you'll get to see them in action some more moving along here. In the next lecture, I'm going to kind of follow a very similar process to what we did with exponential functions and take a look at the logarithmic functions graph.